Good evening, everybody. So I've started the recording for tonight. Okay, so let's get started. We left off last time on, we finished example number 1 using the flexural formula to find stresses due to internal moments. So before we start example number 2, does anybody have any questions for me? Before we start example number 2, is there anybody out there?
Good evening, Professor.
Ah, wonderful. At least one person's alive. Okay. Thank you very much. All right, so let's get started with example number 2. And we'll use this here. Okay, so example number 1, if you recall, we were looking at a beam that was 2 inches wide by 4 inches tall. We applied a moment to it, and we found what the stresses were at the top and at the bottom of that beam. Now we're going to look at a slightly more complicated shape. We're going to be looking at a T-section, and we need to find what the stresses are due to an applied moment. So we're going to use the same moment, 14 kip feet, which is 168 kip inches. We need to find some section properties. So the area of this is going to be a 1/4 plus a 4/1. So a total of 8 square inches. Now to find y bar, this is what we did in our, what was that, our geometry section, our section property section of this class, where you take the area times the centroid of part 1 plus the area times the centroid of part 2 divided by the total area gives you a y bar center of gravity of 3¼ inches up. And I measured everything from the lowest point from this reference line here. I would suggest you do the same. There's no reason that you can't measure y bar from any point. You can measure it from the top, you can measure it from the bottom, you can measure it from down here somewhere. It doesn't really matter, but it's a lot easier to keep track of it and a lot easier to compare answers if you just adopt the habit of always just taking it from the lowest point and find what y bar is from the lowest point to the center of gravity. So here is my coordinate system now. From the lowest point to the center of gravity is 3¼ inches. And if you take 4 plus 1, the total height of this section is 5. 5 minus 3¼ is 1¾ Okay, so everybody following along where the center of gravity is?
Yeah.
Okay. Okay, so the next step is to find the moment of inertia. And the moment of inertia is going to be I got 2 pieces. So each piece, you find the moment of inertia about its own centroid. So if this top piece is 4 inches wide by 1 inch high, then the moment of inertia about its own center of gravity is going to be 4 times 1⁵ over 12. Plus you add to that the area of piece number 1 times the distance from the centroid of the piece to the centroid of the whole section. So I have 4 times 1 times 4½ That comes from 4 plus half gets me to the centroid of piece 1 minus my 3 1/4 is to the centroid of the whole section squared. Okay, so these two terms are for piece 1. And then we add these two terms for piece 2. Piece 2 is down here. So piece 2 is 1 inch wide by 4 inches cubed over 12 plus 1 inch wide times 4 inches tall times 2 is the centroid minus 3 1/4 squared. Okay, so is everybody clear on where I'm getting the moment of inertia from?
Yep.
Okay, so when I add all 4 pieces, I have 2 pieces, but when I add all 4 terms, I get 18.17 inches to the 4th is the moment of inertia for this particular piece. And as a side note, the area of this T section is exactly the same as the area of the 2x4 that we looked at last time, but the moment of inertia of the 2x4 was only 10.67. Moment of inertia of the T section is 18.17. And that's the power of spreading these apart, getting the mass farther away from the centroid. It gives you more moment of inertia, more resistance, which of course is the reason why beams, particularly steel I-beams, have all the mass way far away in the flanges, as far away from the centroid as possible. All right, so now that we have our applied moment, we have our center of gravity, and we have our moment of inertia, we can now use the flexural formula to find the stresses at really any point that we want to. So the flexural formula says that the stress at any given point is equal to the negative of the applied moment times the distance from the centroid to the point of interest over the moment of inertia. So for finding the stress at the top here, sigma t, for the stress at the top, I have minus 168 kip inches. Y, okay, now watch this here. The distance from the centroid to the top of the beam is going in the direction of y. It's positive, and it's a 1.75. So y is a positive 1.75, moment of inertia 18.17. Calc this out, you get minus 16.18 KSI. What's the negative tell you?
It's in compression.
Negative tells you it is in compression, correct. So that's the stress right there. That's represented by that horizontal line right there. It's minus 16.18 KSI. Okay, let's find the stress at the bottom of the top board. So this is sigma 1 for lack of any better way to label this. The flexural formula is the same. The moment is the same. The moment of inertia is the same, but y now is different. So y is from the centroid to the underside of that board. So the board is 1 inch thick. So 1 3/4 minus 1 is still a positive 3/4 of an inch. Okay, it's positive because it's on the north side of the x-axis. I crank this out, I get minus 6.93 KSI, so I'm still in compression at the bottom of the top board. Let's find the stress at the bottom of the whole assembly. So the stress down here at the very bottom, and minus mxy over I. The moment is the same, I is the same, but y is the one that varies. So now from the centroid to the bottom of the section is 3.25 inches, but you're moving in the direction opposite to the positive y. So this is going to be negative. any y representing something below the x-axis is going to be a negative y. Crank this through, and I get two negatives produce a positive, and I have 30.05 KSI. And as you can see this is drawn to scale. So as you can see, this is the largest stress. The largest stress on a non-symmetrical section is going to be that extreme that's the furthest from the centroid. Okay, Nicholas has asked, so the bottom of the part should always be positive and the top always negative. If you have a positive moment, then yes. Because remember, that ties directly to our definition of a positive moment. A positive moment always produces negative stress at the top, positive stress at the bottom, which is compression at the top, tension at the bottom. But you can have a negative moment. If you have a negative moment, then it is reversed. It's the opposite. Okay, so now we're going to test that our rule number 2 has been adhered to, and we're going to sum the forces in the x direction. Okay, so the compression block of this, I've subdivided into segment 1, segment 2, segment 3. The tension side is segment 4. So I've just broken it up into easy to read triangles and squares. Why do I need 3 pieces for the compression? Isn't this just one big triangle? Why can't I just use one big triangle?
They have different stress in each. The top and the bottom is different.
You're on the right track, but it's not the stress that's different.
Area.
Area. 1 and 2 are on this big fat wide board. 3 is on this skinny board. So I can't combine them into the same triangle because this stress is acting over this area and this stress down here is acting over this little area. That's why I had to break it up. Okay. Did you assume y equal to 1.75? Mustafa, I don't understand your question.
I mean, from where like you got these points?
Are you talking about these numbers here, or are you talking about 1 and 2?
When you got the stress at T and 1.
Okay, the stress at T is right here, 1.75 inches from the centroid. And the stress at 1, which is just my dumb label for the underside of this board, is 1.75 minus the thickness of the board, 1 inch, is 3/4.
So it's given.
Yeah, it's given by the problem. Well, no, it's not given. You had to calculate this 3.25 here. And once you calculate the 3.25, which is this dimension right there, that's what you calculated here. Once you have this dimension, then it's trivial or easy to calculate the distance to any other point. And that's all we did. Okay?
Yeah, thank you.
Okay. All right, so I'm going to find, what I'm looking for is the force resultant of each one of these segments, segment 1, 2, 3, and 4. So segment 1, the stress at the very tip here is 16.18, minus 16.18. And the stress here at the bottom is this sigma 1, that's 6.93. So the difference between the two is 16.18 minus 6.93 gives me the magnitude of this line here times an area of 4 wide, 1 high, and then I got a half in here because this is a triangle. So I am just finding the stress times this area to find the resultant. And the resultant is minus 18.5 kips. And that's just for triangle 1. For area 2, which is now the square or the rectangle, area 2, the stress magnitude is minus 6.93 times an area of 4 times 1 gives me minus 27.72 kips. For area 3, now we're talking about this little triangle, the stress magnitude is 6.93 KSI, negative. The area is going to be this little sliver right here. So the height of the board is 4, goes here, minus the center of gravity, 3.25 is here, times a width. The width is given as 1, and again times half because segment 3 is a triangle. So I add it all together, the stress times area, and I get minus 2.6 kips. And lastly, area number 4. Oh, I'm sorry, before I do that, I add all my compression. My compression equals 48.82 kips. Now area 4. Area 4 is a positive 30.05 KSI times a height of 3.25 times a width of a half times a half for the triangle, and I get 48.83. Okay, so 48.83 minus 48.82 within round off error of my calculator is basically equal to 0. Therefore, we have proven that rule number 2 has been abided by. The sum of the forces actually do equal 0. Any questions on what I've done here? Okay. So then we're going to look at sum our force, our moments, sum the moments to see if they equal 0. And we have, okay, so what I did is I found the moment arm, the distance from the centroid to the center of the triangle first. So in order to do that, I did, let's see, number 1 is 2/3 of a triangle and this is 1 inch high, so 2/3 of that, plus the distance from the underside of the board to the center of gravity is the 4 minus 3.25. So you got 2/3 of the 1 inch thickness plus 3/4 inches to get to the centroid, 1.42 inches. The resultant we found is 18.5 kips times 1.42 gives me 26.27 kip inches. And the resultant is in compression, so it's trying to turn clockwise, so it's positive. Part number 2. I have a rectangle now, so the centroid of the rectangle is halfway up. So halfway up the 1 inch thickness, plus the 3/4 to get me to the centroid is 1.25. 27.72 is the resultant that I found, times 1.25 in the clockwise direction gives me 34.65 kip inches. Part number 3. Now I'm below this, so this dimension here is 4 minus 3.25 times 2/3 for the triangle. So my moment arm is 1/2 inch. And the force was 2.6 kips times 1/2 inch, clockwise direction, gives me 1.3 kip inches. Number 4, we have a triangle that is 3.25 high, so the resultant is at 2/3 of that, so 2.17 inches. The resultant of 4 was 48.83. This one is in tension, so it's pushing to the left, which about this centroid is still turning it in the clockwise direction. So I got 105.96 kip inches. So if I sum them all together, 26.27 plus 34.65 plus 1.3 plus 105.96 minus the applied load was 168, and I get 0. Okay, so that's what you ought to get, because the sum of the moments needs to equal 0 for static equilibrium. And what we're basically just proving is that this stress profile, as predicted by the flexural formula, my over I, produces a stress profile that can be reduced to force resultants that meets the rules of sum of forces in the x equal to 0, sum of the moments equal to 0. Any questions on what I've done here? Okay, and so the last thing that I've done here is I drew kind of a bad angle, but this is an isometric of the stress profile for basically this. So this, drawn to scale in isometric, looks like this. And again, the points to pick out here, the neutral axis right there is right where it crosses that plane. And I know that if I could do this in like a solid modeler, I could rotate this for you, but it kind of ended up being a bad angle. But what is also important is that from the side view, you can't really see that every point along the top flange here has the same stress, but this stress is constant. What we found to be sigma t as a stress is constant across the top of the flange. It's constant across the bottom of the flange. It's constant everywhere. So as long as the moment is only in one direction, about x, then there are no moments about the y-axis, then those values are going to be constant. Now, that's not always going to be true. We can have moments about x and about y, and then this constant c will no longer be valid. Any questions on lecture 17?
For the homework, do we need to do the isometric view as well?
Only if the textbook problem asks for it. Yeah,
Yeah, I think one of them asked for sketch.
I think you're right. So if the textbook asks for a sketch of the stress, then that's kind of what we're looking for right there.
Okay.
Okay. All right, so that was lecture 17. Okay, so now we can start today, lecture 18. By the by, so everybody's keeping an eye on the syllabus. We have our second midterm, I believe, is 2 weeks from today. All right, so we're going to start today with biaxial bending. And biaxial bending is adding to everything we just talked about. Everything we just talked about is finding the stress due to a moment about the x-axis, and we use the flexural formula. But it is entirely possible that you have a moment that is about the x and the y-axis at the same time. How do we find stresses? when the moment is not lined up neat and perfectly about the x-axis. Okay, so the first thing we're going to do is, if we have this situation, we're going to resolve the moments. Whatever the applied moment is, we are going to resolve it into an x component and a y component. Some portion of the moment's going in the x direction, some portion of the moment's going in the y direction. And we can say that if the angle is measured from the moment to the positive x-axis, then we can say the x component is cosine theta of m, and the y component is sine theta of m. And so we can take any moment and resolve it into components. Here's an isometric view of what this is showing you. This is looking at the board on the very end. So if you use your thumb in the right-hand rule, put your thumb in the positive x direction, which is to the left, and curl your fingers, and your mx looks just like that. And the x designates that the moment is about the x-axis. Same goes for the y. Take your thumb, shove it up in the positive y direction, and curl your fingers. And you get a moment that looks like this. This is in the positive y, or about the y-axis, thus my. So mx is a positive moment about the x-axis. My is a positive moment about the y-axis. Everybody okay so far? Okay, so here's how we add to our flexural formula. The flexural formula with no moments in the y direction was just minus mxy over I. But when we do have moments in the y direction, then it becomes plus my times x over iy. So this is the correct version. The first term is negative, second term is positive. We can further find the slope of the neutral axis, because the neutral axis is no longer going to be horizontal like it was in the last two problems. Now it's going to be at some slope. So we can find the slope of the neutral axis by saying that the tangent of alpha is a measure of the slope, is equal to ix over iy tangent theta, where theta was the slope of the moment. So in this case, we need both moments of inertia. Yeah, you're going to need the moment of inertia about the x, and you're going to need the moment of inertia about the y. That is correct. Okay, so example number 1. Here is our 2x4. You're going to be seeing a lot of our friend, the 2x4. So here's the 2x4. And I have an applied moment of 14 kip feet, or 168 kip inches, applied at 30 degrees from the x-axis. Okay, so what is my first step is I want to resolve this into an x component and a y component. So the x component is 168 kip inch times cosine of 30. Gives me 145.5 kip inch. My is 168 kip inch times sine of 30, and that's 84 kip inches. So that gives me, and these are both positive. So again, the right-hand rule, this gives me a positive moment about the x and a positive moment about the y. The area of my 2x4 is 8 inches squared. The center of gravity, again, this is obvious, but I just want to lay it out here. 2x4 times 2 inches up divided by 8 gives me 2 inches to the center of gravity. And the center of gravity in the x direction, if I'm measuring from this corner here, is 2 times 4 is the area times a 1 inch centroidal distance over 8 gives me 1 inch. So I do need the moment of inertia about the x and about the y. Moment of inertia about the x means that h is 4 and b is 2. So I have 2 times 4 to the third over 12, or 10.67 inches to the fourth. About the y-axis, when I'm looking at the y-axis, then h is 2 and b is 4. Okay, so h is always perpendicular to the axis. B is always parallel to the axis. 4 times 2 to the third over 12 is 2.67 inches to the fourth. So using the flexural formula, minus mxy over ix plus myx over iy, I would like to find the stress at all 4 corners of my 2x4. As I said before, when we had moments only about the x-axis, then the stress at A is always equal to the stress at B, stress at D is always equal to the stress at C. But if I have moments about the X and Y axis, that is no longer true. Okay, so I use my flexural formula. My moment about X is 145.5. That goes here. Here's my negative. Now at A, what is the y distance to the corner at A? Well, the y distance is the distance perpendicular to the x-axis. So it's this distance here. And is it in the direction of y, or is it opposite to the direction of positive y? In this case, it is in the direction of positive y, so it's a positive 2 divided by the moment of inertia of x, about x. But that's the first term. The second term is a positive 84 my. Now you have to evaluate x. To get to A from the centroid, I have to move horizontally. So I move 1 inch to the left. But is that 1 inch to the left in the positive x direction or the negative x direction? And it's going to be in the positive x direction. So that's why this is a positive 1 inch, because I'm to get to A, I'm going in the same direction as positive x. Divide the whole thing by the moment of inertia over y, and I get 4.19 KSI. This number is positive, so that means that the stress at A is tension. Now, somebody had asked me a little while ago, is the top always negative and the bottom always positive? Only under positive bending moment, but that was only uniaxial bending moment. When you have biaxial loading, you have a mx and an my, all bets are off. In this case, the mx component would have made it compression, but the my component overrode that and made it tension. Okay, so this term overruled this term, and you're left with a net tension at the top of your beam. Is everybody tracking with this? Do I have any questions? Okay. Let's move on to point B. At point B, now from here out, the moment term and the moment of inertia term are not going to change. Those are constant for this section. So the moment and the moment of inertia don't change. The only thing that changes as we go from point to point to point to point, the only thing that changes is y. So for point B, y is still 2 inches, and it's 2 inches up in the same direction as the positive y. So this is still +2. But the second term, I am now going 1 inch to the right, which is opposite of positive x. So my x term is a -1, as you can see here. And I crank this out and I get, whoa, that's a big stress, minus 58.73 KSI. It is negative, so this is in compression. I work my way to C. C, again, these terms don't change. So at this point, we just talk about y and x terms. Y now at C is 2 inches down. It's the opposite of the positive y, so it's -2. The 84, 2.67 don't change, but my x value at C is still -1. I'm going in the opposite direction as the positive x-axis. So I crank these out, and I have minus 4.19 KSI, and this corner is in compression. And lastly, I have my D point, where all these terms remain constant, but my y is 2 inches down, and my x is 1 inch in the positive. So this 2 is negative, the 1 inch is positive. And that gives me a positive 58.73 KSI in tension. Okay, I'm going through this rather rigorously, but I want to make sure everybody is really keying in on how you find the value of y, how you find the value of x as you move around the section.
Emphasize a point. So you're multiplying your coefficients on the top, or are you subtracting them? So for example, stress on A, it's 144 minus 2.
I'm sorry, example at A, okay.
Right. Because when I look on top, the formula on top, it says the moment times y, but you're subtracting for A. Oh, it's Kip Branch.
Oh, yeah, that's
Okay,
not
okay.
Are you okay? Yeah, that's just Kip inch.
Yeah, you're subtracting.
Okay, you're kind of breaking up a little bit. Are you okay?
Yeah, I get it now. I thought you were subtracting the 2,
I
but it makes
gotcha.
sense now.
Okay, okay, sorry about that. Yeah, that's just the way I chose to represent Kip inch. All right, so we basically imagine the moment all around in each sector to find all the different y's, all the x's and y's. You think about this, that the moment is on the whole bar. You basically, you could take this bar and bend it in your hands, and the moment is being resisted by the whole section. But you have different stress at different points because of the combination between the mx and the my.
I have a question.
Sure.
So let's say your M is at section B. Does that mean your MX will be negative 145.5?
No, 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 no. Your moment is not at A or B or C or D. Your moment is on the whole section.
Oh, no. What I meant is like your moment is in the left side, right? When you flip it, let's say it's in the other side, but it's 30 degrees as well.
Oh, okay. All right. All right. So you're saying the moment is this way.
Yeah.
Oh, okay. 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 So what that would do is your mx is going to be negative, but your my is still going to be positive.
Okay. Yeah.
Okay?
Yeah.
All right. So now we can find the neutral axis. We have these numbers. the IX was 10.67, IY was 2.67, and the theta was 30 degrees. So I can solve for alpha is 66.57 degrees. And so what that means is we found the stress at each corner. So I labeled the stresses on each corner. And as you can see, this corner is in tension, this corner is in tension. Any point along the neutral axis is going to be 0. So the stress is exactly 0 along this line. Anywhere that's not on that line will have some stress in it that is more or less than 0. So only along this line are your stresses equal to exactly 0. And this line is aligned at 66.57 degrees from the positive x-axis. Okay, and you can see I drew this to scale, so you can see that the distance from 0 way out to here is almost minus 60, but the distance from 0 to this corner is very, very short. That's why this is only 4 KSI, basically. The further away from the neutral axis you get, the higher your stresses will be. And then this is drawn to scale. And this is, again, the isometric of exactly the same situation as this. So here, the purple line is the neutral axis. And you can see that the stress right there at the intersection of the purple line is equal to exactly 0. The stress right there at the intersection of the purple line is equal to exactly 0. And in fact, if I could shade this surface, where this surface intersects the cut plane is right on that purple line, so it's always equal to 0 at the neutral axis. This stress is equal to way out here, minus 58.73 in compression, and it forms this shape. So this magnitude is 4, this magnitude is 60 almost. Here's your positive 4 and positive 60. So you can find the stress, not just along the perimeter, you can find the stress at any point on this section by using the flexural equation and just plug in the appropriate x and y coordinates to whatever section you want to find the stress at. So for example, I could find the stress, well, maybe like right there, by plugging in the x and the y that gets me to this point. And then if I project it out, that stress would be this point right there on my shape. Okay, so is this reading? Does this isometric help you visualize what we're doing? Is there anybody still alive?
Yeah, that makes sense.
All right, thank you, Stephen. Okay, so now we're going to switch gears. We are going to talk about a totally new subject now. The biaxial bending was not really a whole lecture's worth, so I combined it with horizontal shear. I do see that it's about 6:15 right now, so we'll see how far we get in the next half hour. And there's really no hurry. We got plenty of time to go through these lectures. But we're going to talk about horizontal shear. So the visual example, something that might be a common experience for a lot of folks is if I take two 2x4s and I lay them on top of each other as shown, so that this is a 2x4 and it's on top of another 2x4. If there is no connection between these two boards, they are just literally sitting one on top of the other, then if I stand on this they're going to bend into this shape, as you can see. And when they bend into this shape, you can just see right there and right there that one board is going to slip past the other board. Why is the one board a little bit longer at the bottom than the board beneath it at the top? And that's because what we just learned from bending is that the top of the board is in compression, the bottom of the board is in tension. So the bottom of the board is going to actually elongate and the top of the board is going to compress. So if the bottom board compresses at the top and the top board elongates at the bottom, then one board's going to be longer than the other board. And they're going to slip past each other just like I've shown. So if I take two boards and I stack them to form a 2x8 beam, then the moment of inertia of my total beam here is going to be a 2 times 4 to the third over 12 times 2. So the moment of inertia of one board times 2, because I got two boards. That gives me 21.33 inches to the fourth. That's the stiffness of my two boards just stacked on top of each other. Now, compare that to a 2x8 board. 2 inches wide, 8 inches high. Isn't it exactly the same thing? Don't I have exactly the same amount of wood? But without the separation in here, then if I stand on this board, it's going to take this shape. And this shape has a significantly different shape to it than does this shape. Namely, there's no slip between the top and the bottom half. What is the moment of inertia of this board? One solid board that forms a 2x8 beam is going to be 2 times 8 to the third over 12, which is 85.33 inches to the fourth. My solid board is 4 times stiffer than my two stacked boards. That seems pretty significant, right? That's a pretty significant improvement. So if I stand on the solid 2x8 and this thing deflects 1 inch, then if I try to do the same thing with two 2x4s, it's going to deflect 4 inches. That's the difference between a solid and two pieces. So what is different about the solid and the two pieces? It's called horizontal shear. Horizontal shear is what almost like a glue. If you want to imagine taking these two beams and gluing them together before you stand on it, the glue prevents one slipping past the other. And so two 2x4s glued together or nailed together or in some way connected so they can't slip makes it act like a solid board. And so this illustration here is pulling the two halves apart and looking at the horizontal shear that exists inside of the material that keeps one half of it slipping past the other half. Horizontal shear is what holds the parts together so that it works as a continuous beam. Okay, so everybody kind of get the visual, the mental picture of this, what we're trying to achieve. And we need to know about this also because there are certain types of materials or certain constructions where the horizontal shear between the two pieces might be the weakest link. That might be what governs the strength of the beam is predicated about the horizontal shear. So we have to be able to get our hands around that. Okay, so if I take a simply supported beam with a uniform load applied to that beam, and I look at a little section A to B, then I can pull this A to B element and pull it out and take a look at it. So this blow up right here is this guy right here, this segment from A to B. And what you see here is a positive moment A, and I've drawn it in the positive sense, and a shear, supposed to be shear at A, another typo. And here we have a shear at B, and we have the moment at B. And we have the uniform load on top of this element. What is important here is that A is closer to the midspan. So A is going to have a larger moment than is B, right? And we just drew a bunch of shear and moment diagrams. We saw what the moment diagram looks like for this sort of beam. You know that the maximum moment is at the midspan. So any point closer to the midspan is going to be a bigger moment. Any point closer to the reaction is going to be a smaller moment. So all that to say that the moment at A is going to be larger than the moment at B. Here, I've drawn the stress profile due to a moment at A and a stress profile due to a moment at B. Top is in compression, bottom is in tension, and sigma A is going to be larger than sigma B because the moment's larger at A than B. So far, so good? Any questions so far? Okay. The sum of the moments has to equal 0. And so you have this uniform load that has a moment arm to B. So the uniform load plus B has to equal A because the moments have to equal 0. That's why the moment at A is larger than the moment at B. Here, the sum of the forces has to equal 0. So the compression is balanced by the tension. The compression over here balanced by the tension. The total sum of horizontal forces is equal to 0. Now what I've done, see the dotted line here? I have separated a portion of this portion of a horizontal separation from some of it about the top and about the bottom. What about Fy? Okay, fair question. What about Fy? Some of the forces in the y direction. That's not really pertinent to horizontal shear, but the sum of the forces in the y absolutely have to equal 0, which means that VB plus a little bit of uniform load is going to be equal to, actually this is VA. VA plus some uniform load is equal to VP. So the sum of the forces in the y will still equal to 0. But what we're concerned about is the horizontal shear, and the horizontal shear is governed by the horizontal forces. So what I've done is at the dotted line, I've cut this beam, separated it, and I've taken the top half and drawn it down here. So the top half, you see the stress profile here is this stress profile. The stress profile here is this stress profile. And as I said, sigma A has to be larger than sigma B. So the resultant of the stresses Fa has to be larger than the resultant of the stresses Fb. If I sum all the forces in the x direction, then Fa minus Fb minus, now we need this tau. This is a shearing stress. And this tau is what is horizontal shear. This tau of the horizontal shearing stresses times the area of this surface is what balances the equilibrium for this whole piece. So FA is larger than FB, so I need this tau horizontal shearing stress to balance everything so that it equals 0. So I look at this segment again in a slightly different way. Here's my sigma A, sigma B, here's my tau, horizontal shearing stress, and I need this to bring everything into equilibrium. So the sum of the forces is equal to 0, and we dive into some calculus. Do I have any questions before I do this derivation?
Do we randomly choose where to cut it horizontally?
For this demonstration, it is randomly chosen. This is an arbitrary point, and that's a great question. But in the real world, there are reasons why you would choose where you're cutting it. Those reasons may be that you may want to look at it where it's at its maximum. The horizontal shearing stress would be at its maximum at the neutral axis. That might be a place to check it. Or you could have like a flange and a web that are like in wood, so they'd be nailed together. And you would want to check it at that interface between the flange and the web where they're nailed together, because that's where it's going to want to fail. So it's going to be more obvious a little bit later where you want to draw that line.
Thank you.
Yep. All right, so let's get to a derivation here. On the left-hand side, I'm summing my forces in the horizontal. On the left-hand side, if I take the integral of the differential area, so this is this area here, times my stress at A, that is the resultant force at A, minus the same thing over at B is my resultant force at B, minus my shearing stress times B, which is the width of the element, times dx is this differential length here. So B dx is the area of this underside surface. So this is the most general form of summing of the resultant vectors at A, at B, and the stress underneath here that keeps everything in balance. So B is the width of the shear plane. In this illustration, B is in and out of the page. Okay, so since stress is equal to minus my over I, which we just learned, then I can substitute for my stress here and here, I can substitute my moment at A, my moment at B over I, Y, and Y. Okay, and this is important because Y is part of the variable of dA. So I have just made that substitution here and here. I still have my horizontal shearing stress here. Okay, now if I say that the moment at A minus the moment at B is my dm, my differential moment, that is just the difference in the moment between these two edges, then I can simplify this quite a bit, because my MA minus MB can be brought out in front of the integral, because those are not variables with y, those are constants to this whole side. And so I can bring those out and simplify. So I can just say dm over I times my integral y dA is equal to tb dx. And I took my, not t, tau b dx. I took this term to the other side. And then I can solve for tau. So tau, I just took all this and divided under here. Tau is equal to 1 over IB dm dx. Okay, so now I have a differential moment per differential span, dx, and integral A y dA. Okay. Since dm dx, that's the slope of the moment diagram, is equal to the shear. That's what we learned in our graphical method, that the dm dx, the slope of the moment diagram, is equal to the magnitude of the shear. And we can say that q is equal to the integral y dA, which is actually the centroid of y times a, the area. This is a new term that I'm going to expound on called q. It's called the first moment. But by making these substitutions of dm dx is equal to the shear v, and the integral of a y dA is equal to q, then tau, the horizontal shearing stress, reduces to this very simple VQ over IB equation. And this is what we're going to work with here. Any questions so far?
Oh, isn't it MB minus MA? That's negative MA minus MB.
Okay, this is negative. This is negative. MA minus MB is DM. Somehow my negative goes away. Let's see. So this would,
What I mean is MB minus MA. Because it's minus and then minus MB as well.
I got to write it down on a piece of paper.
Okay.
I know the answer's right because we're going to get to here. That is not going to be minus. So I know the end game. Just let's see. M minus MA plus MB equals tau. And MA minus MB. So that would be minus DM. That would be minus DM is equal to tau. Okay, so since stress is minus y, you got me stumped. I have to look at that one. I got to see where that negative went. Adriel, you stumped me. I don't know. I know it goes somewhere. I know it goes bye-bye.
Okay.
But I have to get back to you on exactly where did it go bye-bye, because I see your point that this is the opposite of this.
Yeah.
And this is positive because it goes over there. I don't know, but I don't want to take up the
Yeah. Okay.
last 11 minutes that I have trying to figure it out. Yeah, no, it's a great question. It goes bye-bye somewhere in here, but it doesn't change this. This is the fundamental answer. Yeah, there's no negative because you said so. Yeah, let's leave it at that for now. All right. So this equation is the horizontal shear equation. And this is what we're going to do our problems with. So all of this was a derivation to get to this. And in this equation, tau is the horizontal shearing stress at a point X on the span. So somewhere on the span X is where we're evaluating this, and it's at some point Y above or below the neutral axis. So it actually has to be located by two coordinates. It's somewhere on the span and it's somewhere up or down in the section, okay? V is the shear force at that section on X on the span. So the shear is a function of where on the span are we talking about. That would be X. So wherever on the span we're talking about, this is the applied shear. I is the moment of inertia at X. B is the width of the shear plane at X on the span and at Y on the section. That may vary. Not all sections have a constant width up and down the section. And Q is the first moment of the area A, which we will, again, I'm going to elaborate on this quite a bit. A prime is the area above or below Y on the section. And Y bar prime is a distance from the centroid of A prime to the neutral axis. Okay. Let's see, where?
Professor, could you go back real quick?
Sure. While you're doing that, hold on a second. I got to close my office door. Be right back. Okay. Sorry about that. I got a lady about 30 feet away from me vacuuming. Okay, so let's talk about these two mysterious unknowns, these two variables. Q is known as the first moment. There's really just no other way to describe it. Is the first moment. And so what Q represents is the area above the shear plane. So if I think it was Stephen who asked, how do you know where to cut it? We'll talk about that more. But if the shear plane, if that cut is here, located at a distance y from the neutral axis, then A prime is the area above the shear plane, and Y bar is the distance from the neutral axis to the center of that area. And Q then is the area prime times Y bar. That's the definition of the first moment. Okay? For the moment, don't worry about how I determine where Y is for the moment. Just that for this particular moment in time, Y is arbitrary, but wherever that shear plane is, that then defines what A prime is the area above it, Y bar is the distance from the centroid of A prime to the neutral axis. Okay, any questions about that? Okay. Now, Q, the first moment, is numerically identical if A prime is taken from above or below the line, the shear plane, at Y. So this A times this Y, oops, I didn't draw the other illustration. Okay, let me go back. Okay, so what this is saying, I can augment this by just drawing in something here. I'll use that. Come on, buddy. That. Oh, there we go. Okay. All right, so the hatched area times this distance is numerically identical to this area that I just boxed in times the distance from the center of that to the neutral axis. So Q is the same if you do the hatched area times y bar is going to be exactly the same number, if you did it right, as this area times this distance. So you can find Q from above the shear plane, you can find Q from below the shear plane, and they will be the same number. Okay, and so I have some examples that will show that. Here is my buddy, the 2x4, and I'm determining that I would like to find what the horizontal shearing stress is at a distance 1 inch up from the neutral axis. So where I'm cutting it is part of the problem. That's defined as 1 inch up. Okay, so if I look at the area above the shear plane, A prime is 2 inches wide and 1 inch high. So I have a prime of 2 inches squared. Y bar is the distance from the centroid of this area to the neutral axis. So that's going to be, this is 1 inch high, so that's going to be a 1/2 inch plus the 1 inch. So Y bar is 1.5 inches. Therefore, Q is 2 times 1.5 is 3 inches to the third. And by the way, Q is always measured in inches or millimeters to the third. If I go at it from the opposite direction, I look at it from below, it doesn't seem possible that Q below the shear plane is going to be the same, right? This is much, much bigger than this area here. But if I look at it, A prime is 2 inches wide by 3 inches deep, is 6 inches squared. Y bar is going to be, this whole thing is 1.5 inches to the centroid, right? But it's minus the 2 inches to the center of gravity. So in other words, 2 inches gets you to the neutral axis, minus 1.5 inches to the centroid. So the distance from the center to the center is only 1/2 inch. 6 times 1/2 gives you 3 inches to the third, identical. And this is a great way to check your work, because if you get a different Q from above or below, then something has gone awry. So if the shear at this location is 10 kips, then we can find tau, the horizontal shearing stress. Moment of inertia of our friend, the 2x4, is still 10.67. B, the width of the shear plane is 2 inches. And so tau is VQ over IB, 10 times the Q, 3 over 10.67 times 2. I get 1.41 KSI is my horizontal shearing stress at this cut point right there. Okay, any questions? All right, I believe this is chapter 7 stuff. Take a look at chapter 7 when you get a chance. And I see that we are pretty much out of time. So I'm going to call it for tonight, and I will see you all on Tuesday. Everybody have a wonderful and hopefully not sweltering weekend this weekend.
Thank you, Professor.
Thank you, everybody. We'll see you on Tuesday.